All right, and we're back again. So I want to kind of wrap up this little example. We had started with an example of travel times, and we said that people travel to work, and the average travel time for everybody in the population is 38.8 minutes, and the standard deviation of travel times is 11.4. And as we had ended the previous video, we said, let's take a sample of size n equal 36, and let's look at the average travel time for people in that sample. And that would be, if x is the travel time, x bar would be the average for our sample of size 36. And then we had concluded by saying the central limit theorem tells us that x bar will be, because our sample is bigger than 30, our sample is 36, x bar will be normal, and its mean will be the same as the population mean, so that's going to be a 38.8, but the standard deviation for x bar will be the population standard deviation divided by the square root of the sample size, which in this case is 36. And so to write that one more time, this is going to be normal, and the mean will be 38.8, and that's a bit of arithmetic there to do sigma 11.4 divided by 6, which is the square root of 36, but it's 1.9. So that'd be 1.9 minutes is the standard deviation. Now let's just kind of make a game out of this, and let's suppose that I come up with a theory. My theory is red cars, or more properly, people that drive red cars, travel less. Now maybe they don't travel less, maybe they're just smart and they find quicker ways to get there. But I mean, of course, that we're saying red cars have less travel time. All right, so I think red cars travel less time than other color of cars. So to test this, I take a sample of size 36 red cars, and maybe this sample of red cars turns out to have an x bar, an average travel time of 34 minutes. Now, that's less than the average for other cars, but of course, other cars, some people travel more than 38.8 and some are less than 38.8. So this doesn't mean that red cars travel less just because I have a sample of size 36 with 34 minutes for the average travel time. It doesn't mean that really is proving that red cars travel less. But what's the probability that if I just take 16 cars out of the population, I guess not 16, it's 36 cars that we're taking, and for 36 cars that are randomly chosen, I compute x bar and find that x bar is as small as the red cars, or maybe even smaller, as small or smaller than what we observe for the red cars. Well, since from the central limit theorem we know the distribution of groups of 36 cars, the probability that x bar is less than or equal to 34 can be computed using these parameters. And I did that earlier, and this turns out to be 0.05763 to state it to more decimal digits than needed. Now you should verify that, but you know how to calculate that probability. Here's your probability distribution, so you know how to calculate it. Now, here's what I want you to think about. Does this sample of 36 strengthen your belief that red cars are no different from other cars, or does it make you think that, well, perhaps red cars do actually travel less? And I contend that it makes me think red cars maybe do travel less, because the probability, if red cars are just like any other cars, the probability of sampling 36 red cars and coming up with 34 or less minutes travel time for them on the average, that only has a 0.006 probability. That's only going to happen about 6 times out of 1,000. So that's a rare event. That's a surprise. Don't believe in surprises. And so this makes me think, well, this makes me think red cars are different. Now, we'll be working more and more on this notion in the days to come, but I hope this is a good introduction. Thank you.